Hello everyone, welcome to the fifth lecture, which is essentially the last lecture in the discussion of our ninth module, where we are talking about occupancy and motion sensors. And if you remember, this is a course on microsensors and nanosensors. So we started discussing sensors based on thermal radiation, and in the discussion we stopped at heat transfer. We tried to understand how the heat can be transferred from one object to another object, and we have discussed that there are essentially three ways by which this thermal energy can be transferred from one object to another object, and they were conduction, convection and radiation. And we discussed that the convection is essentially centralized to the fluids, which is liquids and gases, right? And we also talked about its availability in the spectra, electromagnetic spectra, and we talked that the thermal radiation is predominantly situated in the mid IR and far IR spectral ranges, right? So a hot object, if you remember the Wien's law, a hot object radiates a large part of its energy in the visible spectra, because the wavelength will shift towards the left, right? Whereas the cooler object, like my body or animal's body, okay, they primarily radiates energy in near, mid and far IR regions, particularly in the for our interest mostly we are talking about mid IR and far IR. Okay, so theoretically we also talked like a thermal radiation bandwidth is actually infinitely wide, right? Because essentially it can emit all kind of radiation, because all the particle which is vibrating at certain kinetic energy has do possess a certain temperature, but the average of it was the temperature. That's what we discussed. So essentially a thermal radiation bandwidth is infinitely wide. Okay, however, when detecting this thermal radiation, the properties of real world sensor has to be taken into account. Okay, and any real world sensor cannot detect this infinitely wide thermal radiation. So every sensor basically can measure radiation only within a limited spectral range or in a certain bandwidth, right? So to determine this total radiated power within a specific bandwidth, the radiant flux density, if you remember the W having the subscript lambda, which was our radiant flux density, we have discussed that in detail in the previous class. Okay, so to determine the total radiated power within a spectral a specific bandwidth, say from a wavelength lambda 1 to lambda 2, this radiant flux density has to be integrated. Okay, so if you integrate this equation, this W equation, where this was equal to this emissivity into C1 by pi lambda to the power 5 e power C2, C1 and C2 were constant, divided by lambda t minus 1. If you integrate this equation, basically you get the radiant power. Okay, and radiant power can be obtained by simply integrating it from lambda 1 to lambda 2, right? So if you integrate this, of course this is a complex equation and it cannot be solved analytically for any particular bandwidth. So its solution can be determined either by numerically or by a certain kind of approximation. Okay, so Stephen Boltzmann law actually talk about the equation, the solution of this particular equation. So so from Stephen Boltzmann law, the approximation for the broad bandwidth when lambda 1 and lambda 2 covers around 50% of the total radiated power is fourth order of parabola, and it can be written as the radiant power phi b naught is equal to A into this epsilon, which was this was our emissivity, okay, into sigma t to the power 4, right? So this sigma is a Stephen Boltzmann constant. Okay, and A is the geometry factor, and this we talked is the emissivity, which is assumed to be the wavelength independent for the time being, but we have discussed that this emissivity of course depend on the wavelength. Okay, so the wavelength of the radiated IR light depend on temperature that we have discussed. The magnitude of the radiation is also a function of the surface property, and this is taken into account in the emissivity. Okay, so we promised that we will talk about emissivity in our today's discussion. So emissivity, if you talk, is a measure of ratio of the IR flux which is emanated from a surface to that would be emanated from a ideal emitter which has emissivity E, okay, or epsilon, okay. And both are at the same temperature, and usually this emissivity is from vary from 0 to 1. Okay, the relationship between emissivity, the transparency and reflectivity of an object is given by this equation. So summation of these three, emissivity, transparency and reflectivity, this epsilon, gamma and this rho is equal to 1. Okay. In 1860, Kirchhoff has found that this emissivity and the absorptivity, the alpha one, is the same thing. So basically this epsilon is equal to alpha. So if you talk about a opaque object which has a transparency almost equal to 0, the reflectivity and emissivity are only two things that remain, because the gamma value is 0. I am talking about a opaque object. Okay. So if this equation will become essentially this value, this epsilon gamma plus rho equal to 1, and since I am talking like this gamma is equal to 0, this epsilon plus rho will be equal to 1, or I can say that this rho is equal to 1 minus emissivity, right. So basically the reflectivity is equal to 1 minus emissivity, particularly for the transparent, for the opaque object, okay, where transparency is 0. Okay, we have seen that the radiant power is equal to A epsilon sigma T to the power 4, and this is the radiant power emitted by a surface which is at temperature T. Okay, but if you see this is being emitted towards certain object. I mean anything which is any radiant power or a thermal radiation which is emitted from an object, okay, it will radiate towards some cooler object, right, which is say in its vicinity. Okay, so it's not a unidirectional radiation. Okay, so this radiant power emitted by this surface, this object surface, okay, which is at temperature T, this is towards infinitely cold space which is assumed at absolute 0 temperature. Okay, so I am assuming that this is being emitted towards a colder object which is essentially at a absolute 0 temperature. Okay, now when I want to detect this, I have to utilize a thermal sensor. Okay, so when a thermal sensor detects this thermal radiation being emitted from a object of our interest, okay, it is also necessary to consider the opposite flowing radiation. Okay, when I say opposite flowing radiation, I mean to say that from the sensor to the object. Okay, since of course this is my object and this is my sensor, this is of course at certain temperature, I don't know, say maybe at 37 degrees Celsius if it is a human which is moving in the vicinity of this sensor. Okay, at the same time this sensor is also at certain temperature, it is not at absolute 0, right. So it is also emitting certain thermal radiation, right. So you have a thermal radiation which is being emitted from the sensor surface as well. Okay, so while for the measurement, for the accurate measurement of the movement of this person, okay, in the vicinity of this sensor, I have to also consider the oppositely flowing radiation which is from the sensor towards the object. All right. So a thermal sensor responds only to the net thermal flux, which is the flux from the object towards the sensor minus flux from the sensor towards the object. Okay, so the sensor will respond to the net thermal flux. Okay, so the surface of a sensor which faces the object, say, has a emissivity say epsilon s. Okay, I am considering this emissivity of the sensor. Okay, and that's why I am using a subscript s. Okay, and therefore its reflectivity will be 1 minus epsilon s. Okay, so this rho s will be equal to 1 minus epsilon s. We have seen just now for the opaque object, right? Since the sensor is partially absorptive, okay, the entire flux phi b naught which is being generated from the object is not absorbed by the sensor, or it is not completely utilized, right? So one part of it, say phi b a, is absorbed by the sensor, and another part, say phi b r, is reflected back towards the object. So there are three fluxes involved here. If you see, I have this object and this is my sensor, okay. The flux which is generated here is say phi b naught, all right. Now phi b a is absorbed by the sensor. So phi b a is absorbed in this sensor, right. Now phi b r is reflected back towards the object. So this is phi b r which is getting reflected to the object itself, okay. So there are these three fluxes involved. Let us see how these fluxes are related to each other, okay. The reflected flux is directly proportional to the sensor's reflectivity coefficient, okay. So or this phi b r by phi b naught is equal to minus rho s. Please note that I am using a negative sign which indicates the direction is opposite with respect to flux phi b, okay. So phi b r can be written as minus rho s into phi b naught, okay. Phi b naught we already know is equal to, we have already seen this equation, this is a epsilon sigma t to the power 4, okay, and rho s we already have seen that this rho s is 1 minus epsilon s, okay. So this phi b r will be equal to minus this a epsilon into 1 minus epsilon s into sigma t to the power 4, and this is the emissivity of the object and this value is the emissivity of the sensor surface, right. This is the essentially the equation of phi b r, okay. This phi b r is the flux which is radiant flux which is reflected back towards the object from the sensor surface, okay. We have seen that this is how it looks, right. Till now let us forget this particular part, let us talk about this part. So this is the phi b naught I am talking about, and phi b r which is coming back to the object itself, and please note that this sensor is at temperature Ts and the object is at T, and for the time being this T and Ts are of course at different temperatures. So T and Ts are not equal. So T is not equal to Ts, all right. So this phi b r I know now, okay. The net flux originated by the object is basically phi b naught minus phi b r. Since I have already taken this phi b r sign already we have considered, okay. So I am writing it phi b is equal to phi b naught plus phi b r, right. So phi b naught I already know that is equal to a epsilon sigma t to the power 4, okay, and this minus a epsilon 1 minus epsilon s into sigma t to the power 4, right. This is the equation of total flux, okay. This is the total flux which is generated at the object. If I am taking consideration, I am taking into consideration the reflected thermal radiation from the sensor surface, right. So if I see this equation, this will be simply equal to a epsilon sigma t power 4 minus a epsilon sigma t to the power 4 plus a epsilon s sigma t to the power 4. These values get cancelled and you get this particular value. So this total flux which is the net flux which is originated by the object is equal to A into emissivity of the object into emissivity of the sensor into sigma into t to the power 4, right. This is the net flux which is originated by the object, if I take into consideration the reflected flux. Okay. Now, depending on the sensor's temperature Ts, the sensor surface radiates its own thermal flux in the same way, which results in the net thermal flux which is equal to this value. Okay. Please note that this till now we have discussed about flux of the object. Now, since sensor is also at temperature Ts, okay, there will be a flux associated with this also. So, this phi SR will be, this phi S naught will be equal to same A epsilon S sigma Ts to power 4, right. Similarly, you have to consider this phi SR in the same fashion that we have calculated for the object, and then we have to calculate the net flux, right. So, this phi S will be equal to the same value, but in a negative sign, and this T of course is at Ts. Okay. Object was at T. So, in this equation it was T, and the sensor is at Ts. So, please mind this subscript S, which is the temperature of the sensor. So, this phi S will be equal to minus A, this epsilon S sigma Ts to the power 4. Now, please note that I am already taking this sign into consideration, the negative sign. So, the two net flux which is originated by the object and sensor are combined into final net flux existing between the two surface, which is denoted by this phi. Okay. So, this phi will be equal to the sensor's flux and the object flux. So, phi is equal to phi b plus phi s. Since I have already taken the sign into consideration, this will be equal to A epsilon S sigma into T power 4 minus Ts to the power 4, and this is the mathematical model for the net thermal flux for between a object and a thermal sensor. Okay. This net thermal flux, as we have discussed initially, will be converted by the thermal sensor into the output signal. Okay. Therefore, if you see this equation, the sensor's temperature also matters in the total net flux calculation, and actually that is converted into output signal. So, output say if it is in terms of say voltage, it also depend on sensor's temperature. Okay. So, this equation that we have just seen is establishes a relationship between the thermal power phi absorbed by the sensor, okay, and the absolute temperature of the object as well as the sensor. Okay. This is how a heat transfer takes place between a thermal sensor and the object, and it is the basis of any kind of thermal radiation sensor that exists. Okay. Now, let us quickly discuss about passive infrared motion sensor. We have seen several active devices, but we have not discussed any passive IR motion sensor. Okay. So, as you know that there are two types of IR motion sensor, either you have a passive or you have a active motion sensor. Okay. And passive motion sensor detectors is very popular, particularly in the security and energy management system, and the PIR sensor which I am using for abbreviation for passive infrared sensor actually respond to mid and far IR region, okay, which covers mostly the spectrum range of say 4 micron to 20 micron. Okay. So basically you are covering a mid IR to far IR. Okay. So, the thermal radiation emanated by the human body is concentrated mostly in this range, and that is why I mentioned that it is very important for security applications, because this kind of sensors or this kind of we sometimes call it thermal cameras, basically they are sensors only, are very useful for intruder identification. Okay, so it can basically map our whole body or our animal's body if the intruder is an animal or so. Okay, so the thermal radiation, as I have mentioned, that from human body is concentrated in the range of say 28 degrees Celsius and 37 degrees Celsius. So mostly for this kind of temperature range, you have a number of detectors available, including thermistors, thermopile and pyroelectric devices. But for PIR motion sensors, mostly we utilize pyroelectric elements because they are very simple, they are affordable, particularly for large volume of devices, and they are highly sensitive in this particular spectra range, and they have a wide dynamic range. So even the temperature of the intruder is even little bit far, the resolution you are not compromising. Okay, so mostly you will find that rarely any thermistor or thermopile is used. Mostly all these devices use pyroelectric kind of detector. Okay, so pyroelectric, if you remember, we have discussed that in module 1 and module 2. They are essentially piezoelectric material. So usually all these pyroelectric detectors are piezoelectric as well, and it responds to thermal radiation. Okay, let us understand this with an example that how these PIR sensors are developed using pyroelectric detector. This figure shows a simplified model of a pyroelectric detector, which is of course is a secondary effect of thermal expansion. We will see how. Okay, so this is the object, and this is the interface at which the thermal radiation will be or this sensor will be exposed to thermal radiation. Okay, so initially the element has a uniform temperature. So the complete at both the side the temperature is TA. Okay, now when IR rays is irradiated at this interface, okay, or at this surface, okay, there is a warming up in the concentrated region wherever this IR radiation has fallen on this sensor. Okay, so say this area is exposed. I just want to highlight that this can be localized. So you may have this kind of shape also if the IR radiation is very specific to this particular area. But usually say this whole region is exposed to say IR light. Okay, this front side gets warmed up. Okay, and because of that there is a expansion. Okay, because of this there will be a expansion which causes along with this IR radiation it also causes some charges. So there is a stress induced charge, and earlier this voltage was 0, and because of this thermal expansion there is a charge which is of course converted to voltage. So this voltage is not now, it's a non-zero value. Okay, so this is basically what you are using is a indirect way of generating charge by this pyro and piezoelectricity phenomena. Okay, so a pyroelectric material generates electric charge when thermal energy flows through its body. Okay, if you remember, we have discussed that these are not the temperature detectors, but it's a heat flow kind of detector. Okay, that's why it can be described as a secondary effect of thermal expansion that we have just talked about. Okay, I also mentioned that all this pyroelectric material are also essentially piezoelectric, means that the absorbed heat causes the front surface of the sensing element to undergo expansion that we have just seen. Okay, so this result into thermally induced stress, which leads to development of piezoelectric charge on the element electrodes. Now please note that you have two kind of basically charges. Okay, one, say few electrons are generated because of this pyroelectric phenomena, and few electrons are generated because of this piezoelectric phenomena. Okay, because along with this when this IR radiation is incident on the surface, there is a thermal expansion. Okay, so this pyroelectric material is also generating some kind of electron, and because of this stress induced induction, there is some charges, which is basically a piezoelectric phenomena. Few charges are generated and both are being collected at, say, this 2 electrodes. Okay, now it is very difficult, or it is essentially impossible to distinguish between these two charges. Okay, which electron has been generated by pyroelectric or which electrons has been generated by piezoelectric phenomena. So basically it is not possible to segregate between these two charges. Okay, and since of course they appear as a voltage. Okay, so it is not possible to distinguish between these two, and that is the negative effect of using a pyroelectric material. But there are certain ways by which we can distinguish between which charge has been generated by piezo or which charge has been generated by the pyroelectric effect. Okay, so this, when the sensor is subjected to a slight mechanical stress from some external force, say due to some sound or due to structural vibration, this electric charges can be generated. And since this is a piezoelectric phenomena, as I have mentioned, it is very difficult to segregate between which charge has been generated because of the vibration or which charge has been generated because of the heat waves. Okay, so to separate these thermally induced charges, which is the essential goal, because otherwise the sensor will have lot of false positive. Okay, so to separate the thermally induced charges from the piezoelectrically induced charges, there has been certain kind of work that is going on. We will see what can be the solution. At least one or two solution we will see. Okay, so pyroelectric sensor in these kind of devices, particularly in the PIR motion sensors, are designed symmetrically. Okay, we will see what is the use of this symmetric device. Okay, so when you have this kind of symmetrically designed pyroelectric sensor, this will be helpful in distinguishing thermally induced charges from the piezoelectrically induced charges, and we'll see how. Okay, so a dual pyroelectric sensor is shown over here. This is a kind of this is a first view of this kind of thing. Okay, so this is a side view, this is, you can see a top view. Okay, the sensing element has a front electrode. So I am talking about this electrode, or in this case I am talking about this electrode. If you are not comfortable with front electrode, you can also call it upper electrode. Okay, and there are two bottom electrode. We will see what is the use of or how it is fabricated. So you see, you have this pyroelectric element. So in this structure, this light blue area is the pyroelectric element, and this is the top electrode. This dark blue is the top electrode, and this two black patches that you are seeing are the black electrode, and it is shown over here. Okay, so I am repeating once again, this dark blue area is the top electrode, a single electrode. These two black electrodes are at the bottom. Okay, and they are two segregated, two different electrodes, and top electrode is only one, or upper electrode is only one, and you have one pyroelectric element sandwiched between this two electrode and one top electrode. Okay, now if you see, this is the identical elements which are positioned inside the sensor's housing. Okay, now these elements are connected to the electronic circuit. We will see what kind of circuit it is. The circuit is in such a way that they generate out of phase signal when exposed to identical in phase inputs. Okay, so if the inputs at these two pairs are in phase, okay, or similar, okay, or in the same phase, the output generated will be in the out of phase, or they can cancel each other. Okay, so interferences caused by this piezoelectric effect or unwanted heat signals are applied to both the electrodes at the same time. So basically what you are doing is you are applying in phase signals. Okay, we have just talked that it is connected to a circuit that when you have in phase signals, okay, you generate a out of phase signal. Okay, so this interference caused by this piezoelectric effect or unwanted heat signals are applied to this two electrodes in phase at the same time. Okay, as a result, they are effectively cancelled because they are out of phase. Okay, at the input itself of the electronic circuit. Okay, so while the variable thermal radiation which will be absorbed by only one element at a time, therefore it will avoid any kind of cancellation. Okay, so this is basically essentially at the input you have two not in phase signals. Okay, means that output is not out of phase. Okay, means that you have certain output at the output of the electrical circuit. Okay, so this kind of arrangement in this case of pyroelectric sensor is known as differential configuration or a differential sensor. Okay, so this differential sensor using this pyroelectric element can be fabricated by depositing two pairs of electrode on both sides of a pyroelectric element. Now each electrode pair acts as a capacitor. Okay, and it can be charged either by the thermal input or by the mechanical stress, by the piezoelectric phenomena also. Okay, now the electrodes on the upper side of the sensor are connected together to form a single continuous electrode. So essentially what you were seeing, this continuous electrode, basically it was also two different electrodes, but it has been shorted. Okay, and that's why it looks like a single electrode. Okay, so the electrodes on the upper side of the sensor are connected together to form a single continuous electrode, while the two bottom electrodes remain separate. Okay, this will create oppositely and serially connected capacitor. Okay, so you have two different capacitors which are oppositely charged and they are connected serially. Okay, or in series. Okay, so depending on the electrode's position, the output signal will have either a positive or negative polarity for the thermal flux. Okay, and depending on the electrode's position, the output can have, if you compare it with some threshold, the output can be either positive or negative. However, this kind of configuration is relative for a simple kind of structure. This is fine. Okay, for a simple sensors kind of configuration it is fine, but in practical cases you have more complicated structures, and these electrodes can be formed in a complex pattern, mostly in the form of interdigitated electrode, because sometime one pair of electrode may not be sufficient. Okay, so for better rejection of the in phase signal, the sensor should have at least say 2 or 4 or 6 kind of electrode. Basically in even number of pairs should be there. Okay, when positioned on the pair alternate for a better geometry symmetry, and such kind of arrangement is, of course, as I have mentioned, is known as interdigitated electrode. Okay, so a symmetrical sensing element should be installed and in such a way that both section produces identical signals when exposed to same external conditions. Okay, so most of the time the optical component, for example a Fresnel lens, must focus the thermal image of the object onto only one section of the sensor. So what I mean to say is, if you see, I am talking about the displacement of this sensor. So you should have certain kind of if I take a side view of this particular area, you have a upper electrode and two bottom electrodes. Okay, and you have thermal radiation. Okay, thermal radiation falling on this, and along with this you have this image forming because of the thermal radiation. Okay, now you should have some lenses, mostly Fresnel lenses are used for this, so that it can focus on only one element at a time. Okay, so at any time the optical component, basically a Fresnel lens here, must focus the thermal image of the object onto only one section of the sensor, otherwise the signals from the image will cancel each other. Okay, and the element generates a charge only across the electrode pair, which is subjected to heat flux. Okay, so this is the image formed and this image is moving. So at one time it is focusing only at one electrode. Okay, although these are connected, they are different. Okay, so this is one and this is second. Okay, so this is first and this is second, for example. Okay. So this element generates a charge only across the electrode pair which is subjected to a heat flux. Say if it is getting subjected to heat flux, it will generate charge only in this region. Okay. As the thermal image shifts from one electrode to the other, the current I flowing from the sensing element to the bias resistor R varies accordingly. Okay. So as this image changes, means or image moves, or the thermal radiation basically moves, okay, this current will change. Okay. Now it changes from 0 to positive, okay, when it is moving from, say, this area to this area. Okay. So it is moving from this area to this area. So this is 0 to positive. When it comes in this area, it returns to 0 and then it becomes negative and finally goes back to 0, and that is what is shown in this figure. Okay. So it started when it was in this area, the voltage was 0. When the thermal radiation comes in this particular area of, or in the first electrode pair, okay, it crosses this threshold window and this voltage is positive. Now when this thermal radiation crosses this area and it comes in this area where the two electrodes are separate, okay, the voltage goes back to 0, and again when it comes here, it again take a negative value and then it becomes 0. That's what this electronic circuit is doing. Okay. So it changes from 0 to positive, return to 0, then negative, then go back to 0, and this JFET here is used as a impedance converter, and it is basically working in a voltage, as a voltage follower circuit. Okay. So this resistance R should be very high. Okay. For example, say a typical alternating current generated by the element in response to a moving person is of the order of certain picoamp. So when I say picoamp, means it's a 10 to the power minus 12 kind of current. Okay. This is very small. Okay. And if the desired output voltage for a specific distance is, say, 50 millivolt, if I take into consideration the Ohm's law, the resistor value should be this 50 millivolt divided by the current, which is of the order of, say, 10 power minus 12. So this comes like 50 gigaohm, which is impractical. Okay. So putting this resistor R of the order of 50 gigaohm is nearly impossible. Okay. Such a resistor cannot be directly connected to a regular electronic circuit, right. So this transistor serves as a voltage follower, and its typical output impedance is of the order of few kilo ohm. Okay. And that's how this electronic circuit, along with the thermal radiation detector, that pyroelectric detectors work. Okay. So this detector range is around of the order of typically 3 to 12 meter, but then it is module dependent. Okay. And field of view can be very high, anything from 90 degree to 180 degree with the use of Fresnel lenses, and typical device, the operating voltages or biasing voltages required is of the order of a few volts. Okay. And the quiescent current is of the order of a few micron or few tens of microamp. Okay. And output can be digital or analog depending on what kind of module you are using. Okay. The advantages of this kind of PIR sensor is they are ultra low power devices. So they do not require very high power, and they are cost effective and can be mass produced because of the fabrication of the pyroelectric elements associated, which can be directly deposited by some means of some PVD or CVD. Okay. The form factor of these devices are compact, but then it comes under in different form factor, and this kind of since direct deposition is involved, they are easy to integrate. Okay. No RF or electromagnetic emission is involved, so they are passive and silent, and the main advantage of this kind of devices are they are immune to visual light variation. So they do not have any kind of interference because of the visual light variation in the surrounding. Okay. So that's why this kind of motion sensors are very crucial for military and security applications. Okay. So with this, we have finished our discussions on the motion sensors and occupancy sensors. We'll come back to these sensors once again in the discussion of module 11 when we will talk about smart building and other things. But in that we will mostly talk about their applications, not their fabrication approaches. Okay, so please, I will suggest that go through this module, particularly when you come to module 11 once again. Thank you.